Okay, let's go ahead and get through our lecture today. This is class 18, and today we're going to be talking about structures and unions. And we'll get to what those are here in just a second. Let's go and get started. All right, so structures and unions are what are called aggregate types. And an aggregate type is sort of like an array, except has a different property. And to understand what that is, if you think about what an array is a group of data or memory spots of some type that are all the same type stored together under one name. So an example of that would be something like this array called temperatures, which has 365 integers. So in other words, it's 365 slots that can each hold an integer type, and they're all stored under this name, temperatures. And what a structure is kind of like that. It's a group of elements, just like this had a group of elements that are all stored together, but the types don't have to be the same. They could be the same or they could be different. So a structure is essentially a way of allowing a user-defined type to be created and used in your program. In other words, you could create a type that has various different elements in it, and those different elements that are in it can be accessed individually, and they can be the same type or they could be a different type. Let's look at an example. All right, so here's an example. Let's say we want to store data about a student in a class or a student at the university. And so somewhere in the information system, you need to store that data. So for example, if we want to make a collection of variables that stored that, you might say, this says with an array, but that really probably shouldn't. We're creating arrays of some of these things, some of them are separate, but the data for a student, let me fix that. Let me just say variables here. So the variables for storing that student look like that. So we have a 16 byte array for the last name, a 16 byte array for the first name, 12 bytes for the social security number, a floating point variable for the GPA, an integer for the number of credit hours completed, and then maybe an unsigned int for the birth year, an unsigned int for the birth month, an unsigned int for the birth date. So the idea here is that you could fill in all of these things. Now notice in this case that we're not using a structure. This is all just separate variables. There's nothing here that we haven't seen before. We're just using separate variables for all this. But the question is, what if I wanted to store data in my program for 1,000 students or 10,000 students? We could make an array of these things, and that would look like this. So in other words, storing information for 1,000 students, we just say, hey, there are going to be 1,000 last names, and each one can have 16 bytes or 16 characters. We're going to have 1,000 first names, and each one is going to have 16 characters. And we do that for all of these variables. Now, in this case, we could do that, and that would work. But there's one thing that's not, actually a few things that aren't optimal about this. And one of them, though, is that the data for any particular student, so let's say index 0, student index 0, the first one in our array, the last name is stored here in memory, and then the first name is stored 16,000 bytes later in memory. And then 16,000 bytes after that, we have the social security number, and 12,000 bytes after that, we have the GPA. And then since each float is 4 bytes, 4,000 bytes after that is credit hours, and that's probably long. So 4,000 bytes after that is this birth year, and so forth. So for any particular student, the data is spread out all over the place in memory. And that's not optimal. It'd be nice to have all of those things stored together in one chunk. And there are a number of reasons for that. Performance, the computer having to get different pages to get the data would slow things down potentially. And also if we wanted to resize that thing, we'd have to like move everything around in memory if we wanted to add another student to that in some way. And so there are a lot of reasons that this is not optimal, but it would work. Now, how can we fix that? And as a reminder, first name is 16,000 bytes after last name. Everything's spread out. We don't want that. So here's what we're going to do is we're going to use a structure. And what a structure is it's a way to group different types of things together as one unit, as its own defined type. So in this example, before we can use the structure, we need to define it. So we're defining it how we want it to be. So I'm going to to define a structure, we use the keyword struct, which we haven't seen before. That's a new keyword. And then we give that structure type a name. And one way to think about this, if you've come to this from other programming languages, think of it kind of like a class, but with no methods. It doesn't have functions in it. It only has data attributes in it. So struct student info is the name of the structure type, and then we have these curly braces, and we put the names of the things in there. Now this looks just like those variables that we had earlier, but these aren't variables that we're declaring here. This is the elements of the structure of this type that we're declaring. And the order that we put them in here is going to be the order that they wind up in memory in that user-defined type. Now, one little bit more information about this is that we're defining a user-defined type here. We're not allocating memory yet. We're just defining the type. Just like in an object-oriented language, you define a class, and then you make an instance from the class later. We're just defining this structure type. And note down here that this is a little bit different, that there's a semicolon at the end of this. And that, unlike with functions and other things, and the semicolon here is needed because this is a statement. This is a statement just like declaring anything else or any other code that you write. So we need to have that semicolon there because this ends the structure definition statement. So that looks a little bit different than other things we've seen, but note that you need that semicolon there. If you can hear that, that's the cat scratching on the wall for no reason. Okay. Now, moving on. So once we've defined that structure, now we can declare variables of that type. We can make as many variables as we want from that, just like you can make as many instances you want from some class. So think about this as we've defined a new type. Now we can use that type to create variables. So let's look at how we would do that. So here's the definition of the structure. And then later on in our code, as long as it's after this has been defined, and these are generally defined outside of a function. These could be defined in main at the top, not necessarily in main, but at the top of some source file outside of a function. As long as we define it before we use it, we're good. So notice to declare a single one of these, we say struct and use the name of the structure. And then we use this would be the name of the variable. So this is a lot like saying int I or float f. We're saying create a structure, use the student info type of structure that we've defined previously, and then this is the variable name. So the variable name in this case is single underscore student. And then the semicolon ends that statement where we now have defined it. So this is actually allocating memory for one of these things. And you might say, well, how is it allocating that memory? Well, if you look at this, we have 16 bytes there, followed by another 16 bytes, followed by 12 bytes. So these are not stored with extra padding or it's not stored as like an object. It's really just a block of data like an array, but that block of data has different fields in it. So the first 16 bytes is last name, the next 16 is first name, the next 12 is social security number, the next 4 is GPA, the next 4 after that, or 2 depending on the compiler, is credit hours, the next 4 or 2 is birth year, and then after that is bytes for the birth month and bytes for the birthday. And so if we were to add all of these up, that would be the size of this structure in memory, how much memory does it take. So we've got, what, 32, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64. So across this structure, there's probably 64 bytes allocated to that. And you can see how are they laid out? Like this. Now, there are some things on 32-bit compilers or 64-bit compilers that are done for alignment purposes, where when you stick things in memory, they have to be aligned on 32-bit boundaries in some cases for some architectures. So there are some cases where things will get padding added in or for alignment purposes. But for the most part, these will be in this order. And with things that are kind of multiples of 4 bytes, there generally won't be anything. But if I, for example, had just a single character variable here, it might actually take up 4 bytes before it jumps ahead to this one for alignment purposes. But don't worry about that right now. Just think of this as a block of data that's storing this stuff in it. and it's organized in this order. There's no extra stuff being stored there, or extra object stuff, or a dictionary that has the names associated with some data item. It's actually just a block of data like an array, but there's different parts to it. Oops. And if we wanted to make an array of structures, notice that's really easy to do too. Same way you would declare a variable like int I and then int a to make an array and put square brackets. So we say struct, give the name of the structure, in this case student info, give the array a name, and then square brackets and say how many we want. So this is going to be 1,000 of structures that look like this. And in memory, that's going to store 64,000. This is 64 bytes, and that's 1,000 of those. We're going to have a block of memory here that is 64,000 bytes big that gets allocated for this array. All right, now, notice when you initialize or declare a structure, you can also initialize it. So notice here, if I create this struct of type student info called student1, I can declare that and set it equal to, and the way I do that is kind of like you initialize an array. So we have curly braces, but these have to match the types of the things that are in that structure. So notice we have a character array, a character array, a character array, a float, int, 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 and that matches what we had over here. So that's going to give those structure elements initial values when it creates that block of data. One thing to note is that just like every other thing in C, you can declare pointers to that type. So to create a structure pointer, struct, the type of the struct, asterisk, just like you'd say int, pointer, ptr. We can say struct student info type, that's our type, pointer, student pointer. So this thing here can hold the address of one of these structures, like that looks like this. And to set that pointer, I can use the address of operator on an actual structure to get its address and store it in that pointer. So there's no difference in how structures work and how something like integers or floats or any other type works. It's very consistent. We've created our own new type called struct student info, and now we can use it just like we would to declare variables, to make an array of variables, to get a pointer variable, to point that pointer variable at the address of one of those things. All works very consistently with how everything else works. All right, so the question is, once we have this structure, like the student1 variable, how do I access those individual elements? Because it's got like a last name and a first name and a social security number and a GPA, and it has those little subparts. How do we access those from this? And this is going to look familiar to you. So to access the elements of a structure variable, we use the dot operator. And that dot operator will look familiar if you're used to object-oriented programming. So this is saying in the student1 structure, dot first name, access the first name field of that structure. And in this case, we're just going to do a copy of copying this value, this name, Nolan, the string Nolan, into the first name field of student1. And then for the last name, we can copy that in to access the GPA, just dot GPA. So you notice this looks a lot like what you're used to with objects and object instances with attributes. So it's the same thing, similar concept. Now, if we, whoa, something bad happened there, hold on. All right, so if we have a pointer to a structure, instead of the dot operator, we can use the arrow operator. So if I have this student pointer and it's holding the address of that student thing that we had up here, I can still access the elements of that using the pointer by using the arrow operator instead of the dot operator. So notice just instead of student1 dot first name, we do the pointer arrow, so hyphen greater than, and then first name. So student pointer arrow first name, student pointer arrow last name, student pointer arrow GPA. So notice these are kind of doing an equivalent thing, but this one's using an actual structure. When we have an actual structure, we use a dot. When I have a pointer to a structure, I use the arrow operator. Okay, and then I just said that. So the dot operator is used when we have an actual structure. The arrow operator is used when we have a pointer to a structure. Now you could also get by without ever using the arrow operator or the dot operator for that matter, because they really are just a dereference. The arrow operator just dereferences for us and then uses the dot for us. So really, when I use that arrow operator like this, that's really doing the same thing as if I said, give me the thing pointed to by that structure pointer. And I notice there's a little typo here. Hold on. Should be bar. So it's really, these are two things are doing the same thing. This is saying take that pointer address, get the thing pointed to by that, which is the actual structure, and then get the, now that we have an actual structure that we dereferenced, use the dot operator on that. So these will both work. They produce identical code. There's no difference between doing that and doing this, except this is a little more convenient when you're dealing with a pointer, and you can immediately tell looking at this, oh, that's a pointer that we're dealing with. So it's just a convenience operator. All right, if you use the sizeof operator on a structure that we've defined, it will give you the number of bytes of memory that are associated with that structure. Just like with sizeof int, sizeof float, in this case, sizeof struct of type student info, it'll tell me how many bytes. In this case, probably 64 on your system. And you can also use that on structured variables. So if I created one, I could say, give me the size of that, or give me the size of the array. And that array that we made earlier, if it was 1,000 of those things that are 64 each, we have size of that would be 64,000. So just like with everything else, again, C language is very consistent. Just like with every other type and every other kind of variable that has a type, we can use sizeof, and it will tell me how many bytes that uses in memory. And if that's true, if it's an array or it's a variable, we can use sizeof on it. Okay, memory storage. We mentioned this earlier, but just to touch on it again, the structures are stored in contiguous memory, meaning that if I make a structure like this, I got away from the student one here and used one that's a little more kind of game related. But if you look at that, that structure, the structive type, bolt type. One thing you'll notice is that you tend to capitalize these, just like you do with like classes in a language like Python. And that's useful to have your variables all start with a lowercase, structures start with an uppercase, and that way you can tell when you're dealing with a structure or when you're not. And some programmers will make them all uppercase here. I don't like that because all uppercase is usually reserved for things like macros. And a lot of times you'll see programmers, oh, the cat is trying to hit me now. Go away. But anyway, you'll see some programmers that will name the structure types, like, for example, struct bullet type struct. They'll put the word struct at the end of it so you can see that and know that it's a structure type. But anyway, notice a structure like this has a float for X, a float for Y. Maybe this is tracking bullets moving on a screen in a game. Float speed, float direction, and then a lifetime, so the bullet can disappear after a certain amount of time. Something like this, that would give us 20 bytes of contiguous memory. So 4 for that float, 4 for that one, 4 for that one, 4 for that one, and then 4 for the unsigned long int for lifetime. So if we add all those up, 4, 8, 12, 16, 20 bytes, contiguous memory. Again, no overhead, no extra stuff being stored, no object that has other stuff associated with it, just this block of data organized in this way. And we can also use arrays of structures to make those bigger blocks and index into them, just like with any other array. And later on, what we're going to learn, we haven't learned this yet, but you can actually perform dynamic allocation. So for example, if you have a bullet and then you want to shoot the gun and have 2 bullets and shoot it and have 3, you can actually make arrays that kind of change their size using dynamic memory allocation. And we're going to look at how to do that coming up here shortly. Okay, how do you pass structures to functions? Just like you pass any other type to a function. In other words, you can pass by value, or you can pass by reference. To pass by value, the type of thing that we're passing in, just like you'd put int value, you put the type, which is struct bullet type. The only rule here is this thing has to be defined before we can have it used in this function parameter function argument list like we have here. And then if we're passing the actual structure like that, inside of the function itself, we just use the dot operator on that because we passed in an actual structure. The local name for it we're calling is bullet. So inside of here, we can just refer to it as bullet.x. And these dots, these are not C language. That's just showing there's other code in there. And this is just showing we're accessing that somewhere inside there. There is a dot, dot, dot in C that we haven't learned about yet, but this is not using that. Now, if you pass by reference, then we have the parameter that accepts that, a struct of bullet type pointer. Pointers hold addresses. So this is designed to hold an address of this type of thing. And then since we pass that as a pointer, when we access the elements of that, we use the arrow operator. So again, if we have an actual structure, use the dot. If we have an address of a structure or a pointer to a structure, use the arrow operator. Okay, so that thing up there, and here, let me hide my face so you can see that. So this part up here, notice that this is passing the whole structure, all 20 bytes in this case. So we're passing 20 bytes down here. It can access that with the dot operator. This is just passing an address, which is just, on most systems, like a 32-bit system, that's just going to be 4 bytes. And then this is going to just access that where that is in memory without actually moving the whole thing. And that can actually be pretty useful. Passing by reference can be more efficient since we're copying less data to that function. And it can also allow the function to modify the data that's inside of that structure that we passed the address to. In this case, we passed a pointer to the bullet, and this is going to update that position, and we're going to actually have that now updating that position, the X and the Y, and based on the speed and the direction or whatever. You can see that updating it right down here. Okay, so structures, they can also be returned from functions as a structure or as a pointer to a structure. So to return an actual structure, we might make a function here that's called create new bullet, and that's going to create a structure and return it to us. So in other words, this is almost like a factory that can create bullets. So you say, hey, create a bullet. I want it to be at this X and this Y and this direction and this speed. And that will actually allocate the memory for one of those structures and then return it. And in this case, it's returning an actual copy of those 20 bytes that were allocated in here. And now we can use that in our code by saying, in our main program, we'd say, have some structure to receive that. You say bullet, new bullet, whatever we call it, equal. Create new bullet, pass the stuff in, and that structure will now be assigned to the one that we assigned it to. And ANSI does support structure assignment. So if you have 2 different structures, and these are actual variables, you can say assign the contents of one to the other, and it will automatically copy that block of memory. In our case, if this was bullets, it would copy all 20 bytes. If this was a student type, and that's a student type, it would copy all 64 bytes over this. And in that case, this is showing how to use that. So here you can say bullet 1, that would have to be a structure that was already previously allocated. We can say set that equal to whatever structure this create new bullet function, which we had up here, returns. So the return structure is going to get assigned to this one. The values are all going to get copied into that. Okay, so that's it for structures right now. We're going to be using those more going forward a little bit later on. But I want to talk, there's another thing that's closely related to structures, and so I want to go and cover that tonight. And it won't take long because it's very closely related to structures, but they're also a little bit different. So that concept is a union. And a union is similar to the structure and how it looks when we define it, but they work differently the way they're stored in memory. And the difference is that the member elements of a union, rather than being one after the other, like a structure where we have bullet X, bullet Y, the direction, the speed, the lifetime, all one after the other, the union members are all like using the same block of memory. They're all overlaid on top of each other. And that might seem weird because when you write to one, it's going to overwrite the data of the other ones. And if we write to one of the other ones, it's going to overwrite the data that was there before. So that might seem strange, but it can also be useful. And the reason that that can be useful is that with the elements sharing that same space in memory, unions provide a way of using or interpreting the same memory in different ways in different situations. Now, this will make more sense, I think, in a second when we look at some examples. So let's look at an example here. So here's an example union, and this one isn't really necessarily useful for anything, but I say union U1. That's the name of it, just like you said struct and give the structure a name. I'm saying union and giving the union a name. And then down here, that's saying that we have inside of that union, one of the ways we can look at that memory is as an integer called I, a long integer called I, or a float called F, or a character array that's 4 bytes big. And you'll notice that all of these are 4 bytes the way we have it right now. That's a 4-byte integer, 4-byte float, a 4-byte character array. So this is giving us different ways to look at that block of 4 bytes. I could say, hey, look at it as if it were an integer, look at it as if it were a float, look at it as if it were an array of 4 bytes. So we can create an instance of that union just like you do with a structure. You say union, give the type, and then give the variable name. So this is the variable name, this is the type. Now if I say single union.f, notice this looks a lot like a structure, but it's this union we just allocated up here. Set it equal to 3.1415. We're accessing it through the float pattern of using those bytes. And now notice here though, I could say the memory of %f as an int looks like %d. And I could say access it as an f to pull the float out of it, access it as an int, a long int to pull the integer part out of that. And you might think, well, where are the cases there where this is useful? We'll look at that here in just a second. But before we do that, a couple notes about unions. All the memories or the members are sharing the same memory. They're all overlaid on top of each other. And so that means the different elements just interpret or access that memory according to what type they are. So going back here for a second, if I access it as an integer, remember, memory is just bits. It's just patterns of switches being on or off. In this case, we have 32 switches. And I could say, interpret those 32 switches using this I element. In that case, it looks like a long int. Or interpret it as a float, in which case it's going to show up as a floating point number. Or interpret it as an array of 4 bytes. Each of the 4 bytes, 8 bits each, treat them as individual bytes. And one of the things about that, in this example we had back here, these are all 4 bytes. But if we do have different sizes for those elements, the compiler will automatically allocate enough for the largest of the elements. So whatever the largest is, that's how much the size of that union will be. And if I have shorter ones and access those, it'll just ignore the later stuff in memory. All right, so why use unions? There are a couple reasons here. One of them is interpreting data in different ways. For example, do we want to access individual bytes? Or do we want to access it as floats? Or do we want to access it as an integer? We can set up a union and then we can access it any of those ways depending on how we need to given the situation that we're in. The other reason for using unions is you can create a single type that can hold data of different types depending on what your needs are. So that's like a variant record in another language or a variant in another language where it kind of has a type. The type would be variant, and it can take on or you can use it as different types in different parts of the program. And I've used that for example, writing a compiler that needs to store things of different types inside of some sort of a parse tree. Inside of the tree nodes for that, you can store off those things like, in this case, I want to store a float. In this other case, I want to store an int. And rather than having a thing that has float and int, you just overlay it on the same memory. And you can store floats and ints depending on what it is you're storing. All right, let's look at a couple of actually more useful real-world examples here. So example one here, IP addresses. And if you think about what IP addresses are, you have an IP address like, for example, the address for the university, 146.85.1.1. Now that numbers and dots notation is really just representing 4 bytes. 146.85.1.1. Or you might be used to seeing that on the printers at the university. 192.168 or 206.21.94.250 or whatever. Or on your home network, 192.168.1.10. Now, in some cases, though, it's more efficient since it's really that's just 32 bits. It might be more useful to treat it as that unsigned long value for an IPv4 address anyway. Or you could treat it as 4 bytes. So by using a union, we can put it in as this, the numbers and dots notation, into the 4 separate bytes, and then we can access it as the long integer. Or we could put it in as a long integer, just the 32 bits, and then we could access it in numbers and dots like this. And so that is one example. Another example would be something like colors. Like if you think about colors in a graphics SDK or a graphics program, you have like RGB colors, you have RGBA colors, you have a long value for colors that's stored as like a hex number, like 0xFF, FF. That's just a number that gets stuck into there. And then you might want to treat it as individual elements like the red component, the green component, the blue component, and the alpha. And so here is a structure, or a union, I mean, that is for colors. And notice that I've overlaid all these. I could access it through this RGB array. I could access it through the RGBA array. I could access it as a long value. I could access it using this structure that has a red, a green, a blue, and an alpha component. And all of these are really representing the same thing. So in other words, I could stick the value in this long, and then I could read out the red, green, and blue. Or I could stick it in the red, green, blue, and alpha, and I could read it out of this long value or this array up here. And that can be a really useful thing to just treat the color in some parts of the program like a number, treat other parts like the component values, treat other parts of it like these arrays. And so that's another example there. Now, unions are pretty powerful, very useful, because we're only storing that data once, but interpreting it differently depending on our needs in the program. So that's it for today. Actually, I need to fix this. You already should have your exams back. Let me take that out. And I'm going to change this and say, look for the next assignment soon. And so look for that next assignment. There's going to be a new assignment where you're going to do some stuff with multi-dimensional arrays. And then we're going to move on in the next lab after that. You're going to do some we're going to get into some graphics things, and we're going to do some things that are like graphical and you can see things happening on the screen. So look for the next one. That should be posted on the course page. So look for that. And what we're going to do next class is there's a couple other topics that I want to cover. And then next week we're going to have, after that, we're going to have that chance for bonus points. So check your email for that. Okay, so that's all for today. I would suggest you go into C, write some code that uses structures, play around with it a little bit, get used to how those feel. Maybe go back and rewatch the lecture, because all of that stuff is going to end up being very useful for us for the stuff we're going to do going forward and for you in your life. But think about structures like kind of like a class, but you can't have methods in them, only data. And then once you've defined that structure, then you can make instances of it or variables that are allocated from that. And unions are kind of the same thing, but all the elements are all on top of each other to access it in different ways if you want to. And you can actually have unions inside of structures. If you want, you could have structures that include unions inside of them, a structure that has other structures inside of it. All of that stuff is possible. So I'd encourage you to play around with that a little bit. All right, that's it for today. Everybody stay safe. Make sure to wash your hands and don't go out without a mask. And also, one thing that I do want to mention, since today is Thursday, next Tuesday is election day. So make sure that you make some time to vote next week on Tuesday. It's an important duty, and I think it's a very important year for making sure your voice is heard. So get out and vote. All right, that's it.